and F block elements. Okay. We have to have a look at the electron distribution. We get S block, P, D, F, and F block elements. No. If you remember, we said S block elements, these elements, group 1 and 2, what does it mean if they're an S block element? They have electrons in the S sublevel, their outer shell electrons. The P block has got electrons in the P sublevel. The D block have outer shell electrons in the D block and the F block elements. All right. Now, remember we said the pattern of 2, 8, 8 electrons is not entirely true. It works for the first 20 elements. The next model that we use is slightly more complicated. Remember I said if we could open up the shells, if I could cut them open, then I have 1 shell, 2 shells, 3, etc. And I said to you, in the first shell, how many electrons go in? 2. And we say there's space for 2 electrons. They have opposite spins, so they attract, they pair off. The second shell, we said, this is the S sublevel. It has a single S sublevel and 3 P sublevels. It's got place for 8 electrons. It goes 1, 2, 3. Each one will go 1 into a subshell, and then they will start pairing off. All right? Then we said the third energy level has got an S, 3 Ps, and 5 D sublevel. So it's S, P, D. And once again, the electrons as they are, it just carries on. It first goes there and there, then it goes there, then it will pair off. And then we said what will happen? It's going to jump to the 4S sublevel because it's easier to fill that S sublevel than what it is to fill those. All right. And then it will come back and it will fill them, 1 each, and then it will pair off, etc. Okay. It gets quite complicated, but there's a pattern that one can draw to figure out the order. Yeah. Yes. All right. Now, the pattern that you can draw to help you remember how the electrons go in, we can go and write it as follows. Where is my little pattern? Okay. 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, 4F, 5S, 5P, 5D, 5F. Okay, now the electrons go as follows. They fill first the S sublevel. All right? Then the next S sublevel. Okay, have a look. 1, 2, 3, 4. Are you with me? Okay. Then 2P, 3S. So here are my 2P, and there's my 3S. So there, then there, and there. Okay, now here is the 3P, the 5Ds, and the 4S. Okay, 3, 2, 1. So now it goes 3P, 4S. So it is going to go 3P, pairing off. It jumps 4S. It comes back 3D. Yes, 4P, 5S, and they won't ask further than that. But it's just easy. Once you've drawn it, it's easy to figure it. No, they usually just go up until it jumps, and then it comes back to that. And they don't usually go any further than that. Now, when we're going to have a look at the SPD notation, there are two exceptions to this order. Now, your syllabus does not specifically say you must know those two exceptions, but they also don't say it. They say in general, you must be able to do the SPD notation. So now the two exceptions are chromium and copper. I just want to see, maybe I can, I want to make the whole thing smaller. Not going to work. Okay. We have chromium and we have copper. Now, chromium has got 24 protons, and copper has got 29 protons. Okay, so what is going to happen is that if we go and have a look at let's do the distribution of chromium first. I'll draw in my cells. 1s, 2s, 2p, 3s, pd, 4s. Okay, so we have that, 1, 2, 3. We have that, 1, 2, 3, 1, 2, 3, 4, 5. We have one there. Okay, I'm not going to draw the others. Okay, so chromium has got 24 electrons. Remember, they fill the lowest ones first. And then before they pair off, they go 1, 1, 1 until sublevel is full, and then they pair off. So we go 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18. Now, 19, 20, 21, 22, 23, 24. They are each going to take 1, if I remember correctly. Yes. No. That's where the exception comes in. Normally, it would now go up there and fill up that one. It doesn't. It doesn't. There must be 24. We've got 10, 18 altogether. It goes 19, 20, 21, 22, 23, 24. That's the exception on chromium. All right? Yes, it doesn't want to do that. Because it's got to do with the energies involved. Okay, so just accept it at that. So make a note of chromium when you go and learn. All right, that one. And copper is going to go as follows. We also have 1 P S P D and S. Okay, now copper has got 29. Now the first ones that go in goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, it will go. We've got 10, 18. It goes 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Yeah. Okay. It's only chromium and copper that do this. No, it doesn't. It will fill up the S sublevel. Chromium and copper. Yes. No, then they will first go up to that one, and then they will come and fill up that one. Yes. Yes, and then it goes to the P. All right. No, no, no. Say again? I've just said they all jump to S except chromium and copper. So make a note of the exception. Just write a little note in there in your books. Then you should be all right with that. Okay, in your textbooks, Okay, the electronic structure, they explain it there, but it's not that complicated once you've got that. It's only chromium and copper, which are the exceptions. The chances of them asking it is very, very slight. It's just sometimes, you know, they do ask stuff like that, so I like doing it. If it confuses you, just ignore it, because it'll be 1 or 2 marks. Okay, now, from this, they go and say to you, give the SPD notation of, for example, chromium. Okay? There. Give the SPD notation of chromium. So now you go and say to them, we have chromium, and the 1s subshell has 2 electrons. Yes. 2s subshell has 2 electrons. The 2p subshell has 6 electrons. The 3s has 2. The 3p has 6. There. The 3d has got 5. The 4s has got 1. And there is the SPD notation of an element. No, for this, maybe 2 marks. All right? It's not all that difficult. No, it's not that difficult. It's just something new. Yeah. If I said to you, give the SPD notation of chlorine, then we will go 1, 2, it's got 17 electrons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So for chlorine, the SPD is going to be 1s2, 2s2, 2p, 6, 3s2, 3p. We've got 2, 4, 5. There we go. No. All right. Yes, yes, you can do it in the margin that there will be space. Okay, now I go and say to you, give me the SPD notation of a chloride ion. Gains an electron. Okay. Or if they said calcium, which loses 2 electrons. Let's do calcium. Calcium, 2 plus. Let's first do just ordinary calcium. Calcium has got 20 electrons. So, are you with me? Okay. So, 1, 2, we've got 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Not so? Okay. So what, for calcium, the metal, it is going to be 1s2, 2s2, 2p, 6, 3s2, 3p, 6, 4s2. But the calcium ion, okay, because it loses its outer shell electrons. Koros? Yeah. No. It jumps. It takes less energy to form the S. That's just what you have to go and learn. From the 3p sublevel, it jumps to the S and then it comes back to the 5d sublevels. No, it doesn't. It's got to do with the shielding of the shells and the pairing off with a number of electrons, etc. Okay. They won't do it. They won't ask it of copper because it involves something called hybridization that you don't do at all. Okay. No. No. Yeah, 4s1. Yes. No, 10. No. Don't know whose book you've got. Look at the name. Should tell you everything. It's just fine. Just correct it. Can we do what? Argon will have a filled outer shell. Okay, I'm going to do it on this one. I'm just going to use a different color. I'll use black. How many electrons does argon have? 18. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Why does argon not want to make chemical bonds? It's got a filled outer shell. Yes. The covalent bond, they share electrons. What happens is two of these orbitals, I want that one there. Okay. One of them overlaps with another one, and they share the electrons in the overlap. Okay. It's quite complicated. Yes. 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 Then there will be one open. 18, no, sorry. It will fill up till there because that's 18, and then it will go there, 19. Okay. Yes. Yeah. Mm. Mm. No, but it doesn't matter. It doesn't have to be 8. Because the moment you go beyond the first 20 elements, it'll start filling up here. But what happens is, let's take a new board. If I go there, we go. There's 1, 2, 3, 1, 3, 5. Okay, let's say it's going there. We go there. We go there. There we go, there, and then we go there, and then we go there. Very often, now this is a D block element. Can you see that? Why? Because I've got outer shell or the last electrons going to the D block element. What's one of the properties of the D block elements, the transition metals? They have more than one oxidation state. Now, oxidation state means the number of electrons they can lose or gain. In other words, the number of bonding places it comes down to. Sometimes copper is +1, +2. It can even be +3. Iron can be +2 or +3. But why? Where does this come from? Well, what happens is the hybridization. It makes 6 similar orbits within one sublevel, and then I will have 4 bonding places, or I can have 2 bonding places, or if I only had 1 there, I might have 3 bonding places, and sometimes it even does other stuff. Do you understand? So the number of bonding places are not fixed on the transition metals. It can differ, but because of the D block that is filled. Yes. For the first 20 elements. Well, technically, it can become more, yes. All right. The third shell can maximum contain, that's 10 plus 8 is 18. The fourth shell has got 7F, so it's 14 plus 10 plus 8. So it can have, 32 electrons. Okay, but it becomes too complicated. That's why in grade 8, 9, 10, we just worked with the first 288. All right. Okay, so, yes, I want to carry on. Okay, now, The next thing that we must have a look at is the bonds that form. Now, what type of chemical bonds do we get? Covalent, ionic, metallic. We did them in grade 10. What is a covalent bond? No. Sharing of outer shell electrons. In other words, something like carbon dioxide is covalent because we have carbon and we have two oxygens. Okay, there's an oxygen and there's an oxygen. Here we have carbon. Carbon has how many outer shell electrons? It's got 4. It's looking for 4. So how many must it share? 4. Oxygen has got how many outer shell electrons? 6. It's looking for 2, so it must share 2. So 1, 2, but it's got how many electrons? 6 altogether. So 1, 2, 3, 4, 5, 6. That oxygen does the same. All right. What does the carbon do? Well, it must share 4, and it's going to share them equally. So carbon is going to go 1, 2, 3, 4. And there we have carbon dioxide, which is molecular, because it is a sharing of electrons between non-metals. You have a double period, eh? Okay. Look, I won't carry on the full double period, but I do want to carry on a little bit. So, molecular substance share electrons between non-metals. Now, what are the properties of molecular substances? Low melting and boiling point. Why? What forces do we have between molecules? Weak van der Waals forces. So low melting and boiling point because they have weak forces holding the particles together. If the forces are weak, it will be soft solids, but usually they are liquids or gases. Are there any charged particles? Free to move? No, so it does not conduct electricity. No, pure water does not conduct. The only exception there is graphite, which does. But that's got to do with the... No, it doesn't conduct. All right. The dissolved salts in it. It's a very good solvent. Okay? And we add chlorine to it and just the mineral salts they dissolve, because any ionic solution will conduct, because you have charges that can move. All right. What is an ionic bond? A metal bonded onto a non-metal. What is the product called? A salt. Okay? But how do we get the metal and the non-metal to stick onto each other? The metal loses electrons. The non-metal gains the electrons. If an atom loses electrons, it becomes positive. If an atom gains electrons, it becomes negative. What force do we have between positive and negative? Yes, strong Coulomb forces. So, what will the properties of a salt be? High melting and boiling point. Yes, good. This is of electricity. Hard, brittle, solid. Yes, electrostatic would also be fine. Strong Coulomb forces or electrostatic forces. Are you with me? All right. How do we show the bonding in ionic substances? Remember, with the molecular substances, it's a sharing of electrons, so the outer shells overlap, and we only show the outer shell electrons. But with ionic substances, we have to show the bonding slightly different. So if I said, no, don't take copper sulfate. because the sulfate ion, the structure is complicated. They won't ask that of you. But copper chloride I can take. Okay? So copper chloride, we are going to have copper will have 2 outer shell electrons. Yes, they won't ask this one either, because it's a transition metal. Do aluminium chloride. Oops, 3. Okay, so aluminium in its outer shell has got, well, in a moment, and let's do chlorines. 3 of them, 1, 2, 3 of them. Each chlorine has got how many electrons? 7. Yes, 7. I'm going to do it now. 1, 2, 3, 4, 5, 6, 7. Okay, now, aluminium has got 1. And then I just want to 2, 3. Okay, so what is going to happen is you must show that aluminium is going to, come on, do that, that, and that. So you have to show aluminium is going to lose its electrons to the chlorine. The moment aluminium does that, you show it is plus 3, and the chloride becomes -1, -1. There is the ionic bond. All right. Be careful. Don't show the electron there and there. Then it's wrong, because then you've got extra electrons. They want you to empty the shell and put it in on the formation of the negative ion. Yes. In the end, what do we write? We say aluminium 3 plus 3 chlorides give me aluminium chloride. All right. Any questions on this? Trinitrotoluene or something like that. Ooh. It's probably molecular because it's a liquid. Probably. Yeah. Trinitrotoluene. Something like that. I'm not exactly sure. Okay. Yeah. Why do you have? Because the formula tells me I have 1 aluminium and 3 chlorines. Okay. All right. People remember that we can get double and triple bonds. For example, the oxygen molecule. Oxygen has got 6 electrons in its outer shell it's looking for. 2. So each oxygen will share 2 of its original 6 electrons. The other one does the same. So here we find we have a double bond. In comparison to something like hydrogen, with 1 electron each, which one would be more reactive, hydrogen or oxygen? Hydrogen. You have to break 1 bond, there you have to break 2 to get the stuff to react. Because it supports combustion, it's just a chemical process. If I have nitrogen, nitrogen has got a triple bond, it's got 5 outer shell electrons, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Our atmosphere, 4/5 nitrogen. Why is our atmosphere stable? Very difficult to get it to react. You must break 3 covalent bonds before you can make it react. All right. Yeah? I don't know. It's special oxides of nitrogen. No. The chemistry of nitrogen and its oxides, it forms a separate subunit. Because you get oxides of nitrogen, just the simplest one is NO2, you get NO and you get N2O. That's dinitrogen oxide, nitrogen monoxide, nitrogen dioxide, and you get a nitrate. as well. No, nitrous, I think it's one of those. I think it's this one. Okay. It's complicated, and I'm not up on the chemistry specific of the oxides of nitrogen. I want to carry on with some new work, irrespective of our nitrous burns. One of the things with the oxides of nitrogen, nitrates, for example, when you heat it, it gives off oxygen, and oxygen supports combustion. That is why they add it to crackers and stuff, because it helps the combustion process along when it decomposes. Now, I don't know if nitrous oxide also does something like that, which will help with the combustion, because then there's extra oxygen available for the process. But I don't know about the chemistry of that, okay? Yes, they convert them to nitrates, and from the nitrates make nitric acid, then they make salts, the nitrates. Yes, and they make ionic compounds from it. Yeah. It's a polyatomic ion, ammonium phosphate. It's just polyatomic ions. I want to carry on. You've done them in grade 8, you've done them in grade 9, you've done them in grade 10. Ions, polyatomic ions, carbonate, sulfate, hydroxide, phosphate. We'll get to them a little bit later on. Yes. You just go and learn them, yeah. That you're still just going to go and learn them. No. No. Depends on the oxidation state of the sulfur or the carbon or the nitrogen that it will form, whichever product it does. It depends on what it reacts with, how much energy is available, etc. Okay, now, people, with covalent bonding, we get something known as a coordinate bond, or also known as dative covalent. All right? Now, a coordinate or a dative covalent bond, it's a covalent bond. In other words, there is the sharing of electrons. But normally, when we did covalent bonding and there was a sharing of electrons, if the one atom gives one electron, the other one must also give one, and then they form a pair. And that's where the sharing comes from. Now, in a coordinate bond, we find that the shared electrons come from one atom. For example, you know the structure of ammonia. It's nitrogen and 3 hydrogens. Yes. All right. If I draw in the electrons, hydrogen has got 1, which it shares. Nitrogen has got 1, 2, 3, 4, 5. Now we can get something, this thing is NH3. But we get something with the formula NH4, the ammonium ion. Okay? How does this thing form? Well, what happens is, it depends on what there is. If there's, for example, an acid. In an acid, we have got so-called hydrogen ions. It simply means it's a hydrogen atom which has lost its one outer shell electron. All right? And what happens is, this one wants to form a covalent bond, and it goes and sits there. And once that bond has formed, the whole molecule is positive. We cannot distinguish this bond from any of the others. It's the same strength and it looks identical. This bond over here is a coordinate or a dative covalent bond. Hydrogen has lost an electron. Yes. Okay. The other one that likes forming this coordinate bond is water. Now, water has got 2 hydrogens and 1 oxygen. Hydrogens each have 1. Oxygen has got 6 electrons. There's the oxygen. So in an acid-base reaction, where protons are transferred, the hydrogen ion that we usually write in an acid-base reaction, let's say I say hydrochloric acid breaks up and it forms that plus that. This thing is actually a proton attaches to the water, so I have a hydrogen ion floating about, and it goes and it climbs on there, and there is the H3O hydronium or oxonium molecule. Yes, that is a coordinate or a dative covalent bond. Both the shared electrons come from one atom only. Now, the terminology, yeah. Yes, well, technically, I suppose it could. It's not impossible. Okay, now, this element that supplies the electrons, in this case it was the nitrogen, or the ammonia part, the nitrogen on the ammonia, and in this case the oxygen on the water. The one that supplies the electrons is known as the ligand in the coordinate bond. The ligand supplies, we talk about a lone pair of electrons. So the ligand is the one with the electrons. When you go and look at your blood, hemoglobin in the blood, the hemo part and the globin is a protein part. Now on this hemoglobin molecule, there are specific positions for the transport of oxygen. The oxygen attaches by means of a coordinate bond. In the second column, just above the heading, the shapes of the covalent molecules, we'll come to that in a moment. But there, in those last 2 lines there, they talk a particularly important coordinate. No, water is a weak, sometimes a weak acid, depends on what is in it. You can drink it. You drink vinegar and you drink lemon juice. They've all got them in them. Okay, it just depends on how many of them are present, what concentration. That might make it less pleasant. Probably. Okay, so please just take note, that is the hydronium ion that they talk about. And I want to stop at that point because the next thing is the molecular shapes. And, yeah. All right. Have a look at is the coordinate bonds. Now I said to you, coordinate bonds are formed when one atom gives the shared electrons. The other one doesn't have any electrons. One of the examples was ammonia reacts with a proton to form ammonium plus. The positive charge lies on the whole molecule. You can't pinpoint it to a specific part on the molecule. All right. The other example of a coordinate bond was the H3O molecule. I showed that one to you as well. If we have water, it can react with a proton. It's the proton carrier in the acid base, and it forms as H3O plus, like that. And if I had to draw it to show you Then the oxygen lies there with the 2 hydrogens. Oxygen has got 2 lone pairs, and there we go. And when it forms this molecule, we have a hydrogen in the form of a proton attaching, and the whole molecule becomes positive. All right, but they are fairly simple. It's actually easy to see where the coordinate bond lies, yes? Hydrogen gas is flammable, yes. Yes, then it's molecular. Yeah, this is then it's like this. Okay, this is an ion that goes into solution. Okay. Now, the third one that you need to know of how a coordinate bond is formed is with carbon monoxide, and this one isn't in your textbooks. All right? Now, carbon has got 4 electrons and oxygen has 6. So what happens is, if I have a carbon atom, or take that oxygen and that one carbon, the carbon having 4 electrons is going to bond by sharing one, sharing another, and then, no, I want to do it in black. The oxygen gives the 2 electrons, actually there like that. Oxygen's 1, 2, 3, 4, 5, 6. There we have carbon monoxide. No, the carbon. Oh, I've got it the wrong way around. The carbon. Let me start again. Carbon bonds onto oxygen. Carbon and oxygen. All right. The carbon has got 4 electrons. It's going to bond there and there. And there's the single pair of the carbons. Oxygen has got 6 electrons. 1, 2 form a bond like that. 3, 4, there's a coordinate bond. 5, 6. Sorry about the first one. Okay. So we can have a coordinate bond formed together with normal covalent bonds. All right. Are you with me? So they both have a single pair of electrons in the outer shell, and there is a triple bond holding the carbon onto the oxygen to form carbon monoxide. Yes. No? Yes? It gives a pair, but remember oxygen has how many outer shell electrons? 6. 1, 2, 3, 4, 5, 6. Yes, once they've been formed, once that bond is formed, you can't distinguish it from the others. All right, but that's to explain the formation of carbon monoxide. It's a coordinate, yes, it's also a bonding pair. All right, a coordinate bond in the carbon monoxide molecule. Okay. Yeah, you don't have to know them all. Say again? Then it's got a double bond and 4 electrons in the outer shell. You with me? Oxygen. We'll do that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. To make a triple bond. To form carbon monoxide. Relatively, yes. It can burn further to form carbon dioxide. Yes. This stuff likes to attach. Because there's a lone pair with which it can attach. On each side. And it attaches by means of a coordinate bond. On the hemoglobin molecule. Yes, yes. Do you understand? All right. Okay. They explain some of the polyatomic ions in your textbook. They're on page 34. All right. There they explain and they show you how H2SO4 is formed, figure 2.33. Just have a look at the structure. The sulfur is the center atom. Onto it bonds 4 oxygens. Two of the oxygens are bonded with normal covalent bonds and 2 are bonded with coordinate bonds. Can you see that? The electrons coming from the sulfur. And then onto the oxygen molecules that bonded with a normal covalent bond, each one takes the hydrogen for the H2SO4. Can you see that? The sulfate is -2 because the hydrogens, if... yeah, okay. Then, okay, that's the sulfuric acid one that they've got there, but that one is not specifically specified. The ones that I've done is what you must know the structure of. The next part, they discuss macromolecules. What is a macromolecule? Macro? Big. Normal molecules contain 1 or 2 or 3 atoms. Water is H2O, 3 atoms. Carbon dioxide is 3 atoms. Hydrogen sulfide is 3 atoms. They are just a few atoms together. When we have macromolecules, then we find that we get very large molecules with thousands of atoms in them. We get 2 types of macromolecules. The one is a polymer, and the other is a giant covalent structure. The definition of a polymer is a long chain-like molecule. Your hair is a polymer, long chain-like molecules. The cellulose fiber, yes, keratin is a polymer. The cellulose fiber in wood, it has a grain. Okay, if you can pull out one of them when you break a branch of a tree, it pulls off a thread. It's cellulose molecules. They are polymers, long chain-like molecules. When we make plastics, we make polymers. Long chains of carbons and hydrogens. And that is why plastic, if you tear it in one direction, it doesn't want to go, but in the other direction it does. It's got to do with the structure of the molecules and the forces holding them together. The giant covalent structures are, the examples we do are diamonds, graphite, and silicon dioxide. And each of them have their own unique structures. What makes diamonds exceptional is the fact, remember, carbon has got 4 bonding places. So when diamonds were formed, each carbon is bonded covalently in 3 dimensions onto 4 others. And each of those carbons in turn are bonded covalently onto 4 others, and it forms a network of covalent bonds holding the atoms together. One single carbon is held by 4 bonds in diamond, and that is why diamonds are so very hard, difficult to break. In graphite, we find that each carbon is bonded onto 3 others in ring-like structures. Okay, there we go. You can, yeah, you should be able to draw it like this. Whoops, no. Wait, yes, it's 1, 2, 3, 4. No. No, no, no. No, 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 no. Well, there we must go. There. I always draw it wrong. There. Okay. So each carbon is maximally bonded onto 3 others. So we have a single bond that is not bonded. Now, these ring-like structures form layers, almost like sheets of paper lying in a stack. All right? What forces do we have between molecules? Weak van der Waals forces. So in graphite, these layers can slide off each other. All right? That is why they use it as a lubricant. And why they use it in pencil lead, because when the friction from writing on the paper rubs off a layer of the graphite. But graphite will conduct electricity because it has a free electron that's not held in a bond. But if we go back to the structure of diamonds, where each carbon is bonded onto 4 others, are there any free electrons? Can diamonds conduct electricity? No. Alright, so diamonds and graphites, we say they are different crystalline structures of the same element. We call them allotropes. Different crystalline structures for the same element. Diamonds and graphite. You need to know why diamond is strong. You need to know why diamonds do not conduct. You need to know why graphite is soft. And you need to know why graphites conduct. They ask this year after year after year after year. Yes. Some of the diamonds have impurities in them. And this is because in the sublimation process, it depends on what is in the trapped atmosphere. Lots of carbon under pressure, it undergoes like a sublimation or a deposition. And then if there is some sulfur or some whatever metals, whatever, then they are sometimes trapped. And that is what makes one diamond more valuable than another. And that is why they also have different colors. You get yellow diamonds and blue diamonds. And, all right, but that's got to do with the impurities that are in them. All right. Silicon dioxide, in your textbooks, we don't have it. Okay. We have that silicon bonds onto oxygen, and then it goes onto silicon and oxygen like that. Each silicon, if it looks, has 2 oxygens. All right. Forming a 3-dimensional structure. Silicon dioxide, sand. Make glass from it. Okay? They don't ask too much on the silicon dioxide one for some other reason. There is another crystalline structure for carbon. It's less well known than diamonds and graphite. They call them Buckminster Fullerene, or just Fullerene or buckyballs. And they are carbon atoms that bond in the shape like a soccer ball, the little patches on the soccer ball that are stitched together. That is what the fullerene look like. This one has got 60 carbons. From these fullerenes, they can produce tubes, and this is where the carbon fiber starts coming in, where they make strong materials with carbon fiber. All right, it's playing around with the crystalline structure of the fullerene and the graphite that makes the sheets. They close it up in a tube. And then you get a very strong structure because it's covalently bonded. Okay, but it's very light because there's lots of air in between. The molecule is not solid. Metallic bonds. With metallic bonds, we basically do positive atomic rest surrounded by a sea of delocalized electrons. What are the properties of metals? Shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. All right? The reason why they have these properties are due to the delocalized electrons. Metals are shiny because the electrons are reflected the electrons on the surface of the metal reflect light. Alright? They are sonorous because the electrons help carry the vibration of the sound through the metal, because the electrons that are delocalized are free to move. They are malleable and ductile, workable. You can hit it with a hammer or you can pull it into threads, because the positive atomic rests have the ability to slide over each other, and the negative delocalized electrons in between maintain the attractive forces. So it doesn't shatter like something else would have. Malleable, ductile, good conductors of heat and electricity. The delocalized electrons carry the charge. Conduction implies energy is transferred from particle to particle. We've done conduction, convection, and radiation. Okay? Metals are good conductors. Non-metals are poor conductors. Why?
Because there's not any delocalized.
Metals are better conductors than the other solids because the delocalized electrons can take the energy and carry it through the metal much faster than what it goes from particle to particle to particle. It does go like that in metals, but it also goes with the electrons, and that is why metals are much better conductors of heat and electricity than what non-metals are, because they don't have the delocalized electrons. I think I'm going to stop there.